Today, we're going to pull back the curtain on one of the most common yet clever components in all of electronics, the potentiometer. It's the simple device that lets us translate physical movement, like the simple turn of a knob, into a signal that circuits can actually understand. So let's dive right in.
I mean, think about it. You've used them thousands of times, right? That smooth, satisfying turn of a volume knob on your stereo, or the slide of a fader on a mixing desk. It feels almost like magic. But what's actually happening inside to make that change?
Well, the answer is this little guy right here, the potentiometer, or as most people call it, a pot. It is the unsung hero of countless devices, a simple resistive sensor that's been turning our physical actions into electrical commands for decades.
So how does this tiny component manage to do such a critical job? Well, it all boils down to a really elegant and surprisingly simple core principle.
Okay, here's the textbook definition, but let's break it down into plain English. A potentiometer is, at its heart, a sensor. Its one and only job is to detect mechanical motion, whether that's a twist or a slide, and turn it into a changing electrical signal. That's it.
Electrically speaking, this is what's going on under the hood. You've got a resistive track, that's the zigzag line, with a connection at each end. But the real magic is that third connection, the little arrow. We call that the wiper. And, as you might guess, it's the part that moves.
And the science that makes this all possible is something called the voltage divider principle. The easiest way to think about it is to imagine that resistive track as a long ramp for voltage. The wiper lets us tap into that voltage at any point along the ramp. So the voltage we get out is a direct reflection of the wiper's physical position.
And this diagram just makes it crystal clear. As that wiper contact moves along the resistive strip, the output voltage changes smoothly with it. If you move it all the way to the top, you get the full input voltage. Move it all the way to the bottom, you get zero. And anywhere in between, you get a value that is a perfect electrical snapshot of its physical position. So every time you turn that knob, the wiper, which is terminal B in this diagram, is just cruising along that circular track. As it moves, it changes how much resistance there is between the input A and the wiper B, and also between the wiper B and the ground C. It's this change in the ratio of resistance that changes the output voltage, which is how the circuit knows exactly how far you've turned the knob.
All right, now that we've nailed the principle, let's look at the two main physical forms these things come in. Each one is built for a different type of motion.
And here they are. On the left, you've got the linear pot, which you might know as a slider. It measures position along a straight line. Then on the right, you have the much more common rotary pot, which, you guessed it, measures rotation or angular position. The principle behind them is identical. It's just applied to a different kind of movement.
You will find these linear slide pots all over the place in audio and lighting control. You know that really satisfying feeling of pushing a fader up on a mixing board to slowly bring in the drums? That's a linear potentiometer in action, translating that smooth, straight-line motion into an electrical signal.
And the rotary version is, well, it's practically everywhere. It's the classic volume knob, the tuner on an old radio, and it's even used inside robotics to give servo motors feedback on their exact position. It is an incredibly versatile and fundamental component for just about any kind of user control. So, they're simple, they're effective, and they're cheap. Sounds perfect, right? Well, like any piece of technology, there are always a few trade-offs to consider.
The pros are pretty obvious, they are simple to use, and they cost next to nothing. But their biggest strength, that physical contact, is also their biggest weakness. Because that wiper is constantly scraping along a resistive track, it physically wears down over time. Ever turned an old volume knob and heard that awful scratchy crackling sound? Yep, that's a worn-out pot. This physical wear means they have a limited lifespan compared to more modern, non-contact sensors.
So here's the bottom line. Despite their mechanical limitations, potentiometers are still an absolute cornerstone of electronics. They provide an elegant and incredibly cost-effective solution to a really fundamental problem. How do you translate our physical world of movement into the electrical language of circuits?
So now that you know the secret, this whole idea of a resistive track and a movable wiper, start looking around you. What about the joystick on a game controller? Or the dimmer switch for the lights on your wall? Where else do you think you might find this simple, clever little position sensor hiding in plain sight?